Have you ever stopped to think about the incredible twisting forces that are, well, pretty much everywhere? I mean, from wringing out a wet towel to the massive engines that power our entire world, there's a hidden science behind the simple act of a twist. So let's dive in and get to grips with the powerful science of torsion.
Just look at this soil auger. You've basically got two forces at war here. The massive power of the engine trying to drive it into the ground, and all that dense, packed earth pushing back, resisting it. That epic battle creates this intense twisting effect all along the shaft. That, right there, is torsion in action.
And that leads us to the most critical question for any engineer or designer, or really anyone who wants to build something that lasts. How much is too much? How can you possibly predict the exact point where a simple twist turns into a catastrophic break? Well, that's the puzzle we're going to solve together today.
Okay, first things first, we need to recognize that this force is absolutely everywhere. Seriously, it's in the drive shaft of your car, the drill bit sitting in your workshop, even in the simple act of turning a valve to shut off a pipeline. Our world is literally full of these twisting forces.
Now, the official scientific name for this twisting force is torque. You can think of it as a rotational force. You know, a regular force pushes or pulls in a straight line, but torque, its whole job is to make something rotate. Or, in our case today, to twist something right along its length.
So what is actually going on inside a material when we apply all this torque? Let's zoom in, way down to the material level, to see what happens when it's put under this very specific kind of stress.
This is such a fantastic way to see that internal change. So, on the left, you've got a simple square drawn on a rubber bar. Pretty straightforward. But look at the right. After we apply a twist, see what happens? That perfect square gets distorted. It's pulled into a diamond shape. This is the physical evidence of the material straining under that load.
And that visible distortion, that diamond shape, it has a name: shear strain. It's literally the internal layers of the material sliding past one another, causing that change in shape. It's the physical proof that torque is at work deep inside the material.
Now, what's really interesting is that this strain isn't the same all the way through the object. This diagram shows us something crucial. The shear strain is zero, nothing, right at the very center of the shaft. It's barely being twisted at all there. But as you move outwards from the center, the strain just increases in a perfect straight line, reaching its absolute maximum right on the outer surface. So the outside of the object, it's doing all the heavy lifting. Okay, so now that we know all that, how do we get back to our original question and actually predict the breaking point? Well, here's the thing. Engineers don't guess. They have a powerful and, honestly, a surprisingly elegant formula to calculate all this internal stress. First step, it just makes sense that the internal stress depends on how much torque you're actually applying, right? The more you twist, the more stress you get. We'll call this variable T for torque. Second, just like we saw, the stress depends on where you are inside the shaft. The farther you get from the center, the higher the stress climbs. We use the Greek letter rho, that's rho, to represent this distance from the center. And finally, the shape of the object itself plays a massive role. Different shapes just have different levels of natural-born resistance to being twisted. This special property is called the polar moment of inertia, and we give it the letter J. You put all of that together, and you get this, the torsion formula. It says that the shear stress, which we represent with the Greek letter tau or tau, is equal to the torque times the distance from the center, all of that divided by the shape's built-in resistance. This right here, this formula, is the key that unlocks our ability to predict exactly what's going on inside. So, let's do a quick recap of the players here. Tau is the internal stress we're trying to figure out. T is the external twisting force we're putting on it. Rho is how far from the center we're looking, and J is that number that tells us how tough that particular shape is against twisting. With just those four pieces, we can calculate the stress at any point in the shaft. It's pretty cool.
Okay, a formula is great and all, but let's see what it can actually do for us. We're going to use it to answer a classic engineering question. If you have the same amount of material, which is stronger, a solid shaft or a hollow tube?
All right, here's our matchup. In this corner, we've got a solid steel shaft with a 100mm radius. And in the other corner, a hollow tube with the exact same outer radius, but with its middle scooped out. For this test, let's say the material in both can handle a maximum stress of 75 megapascals before it's toast.
So, we plug the numbers for our solid shaft into that torsion formula, and what do we get? We find it can handle a maximum torque of 118 kilonewton meters. And trust me, that is a significant amount of twisting force.
And now for the hollow tube, we run the exact same calculation, and its maximum torque comes out to 80.5 kilonewton meters. So there you have it. The solid shaft is stronger. The formula gives us a clear, definite answer, no guesswork involved. It allows an engineer to make a precise choice based on data.
You know, understanding how to prevent failure is one thing. But what's also fascinating is how things fail when the torque is just way too much. It's not always a simple clean snap. This is a perfect example of that. When a wooden shaft gets hit with way too much torque, it doesn't just snap in half. No, it splits right down its length, following the grain of the wood. And that's because that shear stress we talked about is acting both across and along the shaft, and it's always going to break along its weakest plane. In this case, the wood grain. But here's what might be the coolest part. Sometimes, engineers actually design things to fail on purpose. This mangled truck drive shaft is a perfect example. It's designed from the get-go to be the weakest link in the chain, so if the torque gets dangerously high, this part breaks first. It acts like a mechanical fuse, sacrificing itself to protect the much more expensive engine and transmission from catastrophic damage. How smart is that?
So really, the crucial point in all of this is that understanding the physics of torsion isn't just some boring textbook exercise. It allows us to calculate these incredible forces, to predict failure before it happens, and ultimately to build everything from our cars to our power plants to be stronger, safer, and a whole lot smarter.
It all comes back to seeing the world through the lens of science. That twisting auger isn't just a hunk of metal anymore. It's a dynamic field of forces that we can now understand and even predict. Which kind of leaves us with a final thought. What other unseen forces are shaping our world right now, just waiting for us to figure them out?